Okay, today we start with the Euclidean geometry. Now, in order for us to understand it more easily, we just need to look at the terminology of a circle. So, this is a sketch that you should have seen in previous years in mathematics. I'm sure it is not new for you, but because we actually only worked with the center and the radius and the circumference and maybe the diameter, those are the only ones that we are really familiar with because it's the only ones that we used. Right, so there are one or two new ones that I just want us to look at. So you all know what a circle is, their terminology, you all know what a radius is. Then I underlined something there for you. All radii in the same circle are equal in length. Okay, that's very important. I think you know that as well, but just to take note of it again. A diameter is a straight line from one side of the circle to the other and through the center. It must go through the center for you to have a diameter. The perimeter is also called the circumference. We actually refer to it as circumference, and that is the outside of the circle, the distance around it, the circumference. Alright, the next one is something that you know but that we haven't used a lot, and this is an important one, and that is the chord of a circle. Now, a chord is almost like the diameter. A diameter is actually a chord. It's a straight line through the circle, but it doesn't necessarily go through the center like the diameter. Okay, so a chord is just from one side of the circle to the other side of the circle. Now, very important, when you have a chord, it divides your circle into segments. Alright? So, when I look at that line there, thank you. When I look at that line there, it has, or that chord, it has created two segments of the circle. That black part is the one segment and the bottom white part is the other segment. Okay, so that's important because we are going to learn about angles that are subtended. We'll talk about subtend in a minute by a chord in a specific segment. So when I refer to it as an opposite segment from a line here, it would be this side. It's an important part to know. Right. The next one, okay, also already had segment there. Then we have the arc. Now that's one that I want us to talk about as well. So an arc is very much the same, or the application or the use of it in Euclidean is very much the same as a chord. But the chord is a straight line from point 1 to point 2, whereas the arc is from point 1 to point 2, but on the circumference of the circle. Okay, but its points are the same distance as the chord. Then the last one is a tangent. A tangent is a straight line that intersects the circle at just one point. Okay, so it only touches that circle. If it intersected twice, it would be a chord. You agree with me? Because then it would cut a piece of the circle off. Now it just touches it. Now, before we go further, I want us to look at the word subtend. So, okay, it's not here. Let me do it on this page for you. When I have a circle like this, you don't have to draw it, it's fine. I just want to explain the word to you. And I have point A and point B. Just consider. If I were to join them, there's a chord. At this stage, it's an arc, but it makes no difference. Now, who has a little, Karabu has a sister that I know, Mbali. Okay. So, a mom and dad, they had Karabu. Okay. Mom and dad had Mbali. Okay. What this mom and dad is doing, we call it subtend. They make the angle at the circumference. Okay. So when we refer to a chord or an arc, that's point A and B. Doesn't matter if it's joined with a straight line or with the circumference. That is A and B. It's a mom and dad. They subtend child A, or let's call this C, child C, and they subtend child D. Okay, so they are the creators of that angle. That's what it means when AB subtends the two angles. Now, one of the theorems that we're going to learn now as well is when it's the same mom and dad, these two angles will be the same. That one is x, that one is x. If this one is 50, that one is 50, because they have the same mom and dad, subtended by the same arc or chord. Doesn't matter if it's a chord or an arc. It makes no difference. Okay, is that clear? So you understand the word subtend. It subtends it, it's its mom and dad. Right. We have got 9 theorems that we are going to learn about in grade 11. But we are going to divide it into 3 parts. Now for this part, I need you to do your best to pay attention, because this will now just be a whole lot of information that I'm going to bombard you with. Because I'm going to go through all of the theorems, and then we're going to look at the application. So the theorems and their proofs is important. One proof is asked in every question paper, 1 to 2. That's 5 to 6. You don't have this page sheet. I just want you to look here. Okay. We are going to do the theorems later, but I'm going to do it now. So 1 or 2 of them are asked, but because we don't have a lot of knowledge about the terminology and the work that we are doing now, it will be very hard for you to understand the proofs of the theorems now. And it will be, you might understand it, but you won't remember it. Okay. So we are first I'm going to go through the theorems with you, look at the proofs. You don't have to copy. Then we're going to go to the application immediately. Now the application is much easier than learning the theorems first. So then we're going to look at the application. Then we're going to throw all of the theorems together, and then in the end, when we're done, we're going to learn the theorems. Because actually, as a matter of fact, you don't need me to learn a theorem, because you just need to learn it. Does that make sense? Okay. The 3 parts that we divided in is midpoint theorems, cyclic quadrilateral theorems, and then tangent theorems. So the first one is the midpoint theorems, which you all know what a midpoint is. Now the reason we divide it in these 3 is because we have so many theorems. For example, if I give you a question and there's no midpoint on that sketch, drawn on that sketch, is there any use looking for theorem 1, 2 and 3 that needs to have a midpoint? No. So you don't even think about that. If you look at this sketch, a cyclic quadrilateral is a quadrilateral that fits into a circle. So the 4 points of the quadrilateral is on the circumference of the circle. Is there, or are there any 4 points on the circumference of the circle? So would it be necessary or even at all possible for you to look for cyclic quadrilateral theorems in that thing? No. Cyclic quad has got 3 theorems. The third one is the tangent. There is no tangent. Will it help you to look for tangent theorems? No, because there is no tangent. Do you understand why we divide it in 3 groups? Alright, now the first one, the first theorem, has got 2 ways that we can use it. It is about a line that's from the center of the circle on a chord. You see, that's not a radius. It's a line from the center on the chord. Now I want you to just, for this case, ignore these dotted lines, because this is about the proof. The dotted lines are there for the proof. I don't want to talk about the proof now. I just want to explain the theorem. So the theorem says, if that line is on the chord and they tell you that these 2 are perpendicular, then the theorem says, then these 2 lines will be equal. Okay. So if this line from the center goes onto the chord like that, you see now it's not 90 degrees, then this chord has not been bisected. But if the line is perpendicular to the chord, the chord is bisected. We also use it in the opposite way. They can give you the circle, né? You have the center, the midpoint, it's on the chord, and now they tell you, or you figure out in some other way, that that chord has been bisected. What does that mean for that angle? It's going to be 90 degrees. So that one you use both ways. Okay, we call it the converse. Okay, you use it forward and then you use it backwards. So they will either tell you it's 90, then you know, equal sides, or that one has been bisected. Or they tell you, right, that one is bisected, then you know, oh, that one is 90 degrees. Right. The proof of this theorem, just so you know that I am not lying to you, is proven by using congruency. Do you remember congruency? Okay, you see why we're not doing the theorems now, because if I tell you to prove two triangles congruent now, that would take a whole period for you to remember that now. Alright, so I'm just quickly going to tell you. When I do the proof, I put in the dotted lines. We call it, I do a construction. So that wasn't there, I put it in. And then I've got triangle OAP and triangle OPB. And in this triangle, I see that I've got a common side. Okay, so the sides are equal in those two triangles, one of the things. The next thing is that there's a 90-degree angle. It's on a straight line, so the other triangle also has a 90-degree angle. So I've got 90 degree and side. Now, the one that you know from congruency is 90 degrees side. So the other side that will be equal to each other is going to be AO and BO. The reason why they are equal to each other is because it's radii. That's a radius, that's a radius. And you remember, all radii are equal. So because of the 90-degree angle in both triangles, common side and then a side equal because of the radius, I know that those two triangles are congruent. That means they are exactly the same. And that brings me to the conclusion that this side is equal to that side. Ons sal maar môre, ek rekord nou gou, ja, kan nie nou. Ons sal môre nie. Okay, so that's the proof of theorem 1. It can be used both ways. So either they give you the 90 degree, you know the chord is bisected, or they tell you the chord is bisected, you know the angle is 90 degrees. Easy peasy. The next one, this is a proof, theorem 2, that they ask a lot. Okay. This is the angle at the center is equal to 2 times the angle at the circumference. So what that means is, you see the mom and dad? Now they had a child here in 1980. Okay. Then they had another child in 2020. Right. They are the same, but they are too far from each other. The one is already a grown-up, the other one is still a child. So this one here will be 2 times the size of the one at the circumference. The angle at the center is equal to 2 times the angle at the circumference when it's subtended by the same 2 points. Subtended, same mom and dad, created by the same one. Okay, so the proof for this one, it's not a difficult proof, it's just a little bit complicated. You wouldn't have the dotted line. Remember, all the dotted are constructions that you would now know you would have to put in. So when I draw that line, I've created 2 triangles. Now I'm going to say that this angle A and this part of angle P will be equal to each other because of radii. Do you see? Radius, radius, isosceles triangle. Angles, the correct wording we're going to use is angles opposite equal sides. Angles opposite equal sides. Right, and those 2 angles added will give me the value of that angle. Can you tell me why? The exterior angle of the triangle. Right, happy with that? Now I go to the other triangle. This angle and this angle will be equal for the same reason. Radius, radius. And these 2 angles added will be equal to this angle, which is what? Oh, for what reason? Again, the exterior angle. Now do you see P is collicky cross and O is 2 collicky 2 cross. Do you see I've just proven it? This angle is 2 times the size of that. That's the proof. We're just going to use the application. So I'm going to give you this angle. I say 50 degrees. I ask you what's this one, X. You say 100. Why? Angle at the center equal to 2 times angle at the circumference. That's it. That's the application. Much easier. Okay, the next one, number 3, is called angle in a semicircle. Now, it's actually not a new theorem. We get this theorem from theorem 2. Do you see H and K? Is mom and dad, no? They have created an angle at the center. What's the size of that angle? This angle. 180 degrees. Do you all agree with me? Because it's a straight line. Right. Now the angle at the center is equal to 2 times the angle at the circumference in the opposite segment. Do you hear where that segment thing is coming in? In the opposite segment. So if this one is 180, a straight line is always 180. No? It's not sometimes 180 and sometimes 190. It's always 180. What's that angle size going to be? 90 degrees, because the angle at the center is equal to 2 times the angle at the circumference. So its proof would be using theorem 2. But we are just going to use the application. We're going to say A is equal to 90 degrees, and my reason would be angle in semicircle. So, that's it. That's how we use it. Make sense? Those are the 3 midpoint theorems. The next one is the Karabu-Umbali theorem. It's the first cyclic quad theorem. Now you will tell me when you look at this, but ma'am, there is no quadrilateral there. But you need to remember in Euclidean geometry, whenever you've got 4 points on the circumference, that is a quadrilateral. Okay. 4 points on the circumference is considered a quadrilateral, and it's considered a cyclic quadrilateral. Now, you would do a construction to create a midpoint. Okay? So I have an angle at the center, let's call it 2x. What would, you see there's mom and dad, A and B. A and B has the kid in the 1980s, and now it has the kid in 2020. What's the size of Q then? X, because the angle at the center is 2 times the angle at the circumference. Now I want you to ignore that line. Mom and dad has a kid in 1980. It has a kid in 2020. What's the size of that angle? So do you see? Those two subtended by the same chord or arc are equal to each other. And you can go and draw in a million of these. They must just start at A, end at B. In the opposite segment. So not to this side. Not to the bottom, to the top. All of these angles will be X. Because they all have the sibling in the 1980s. So they will have they are the sibling in 2020. Happy? Right, next one. The opposite angles of a cyclic quad. Dotted line will be your construction. You put in the center, you make the construction. Now, I want you to look at O1. No? Let's say this is 2y. Do you see it's an angle at the center? Equal to 2 times the angle at the circumference. So what's B going to be? Y. You see? In the opposite segment. Right. This one, O2, I call 2x. Angle at the center. You see, this is even a reflex angle. That's fine. It's not subject to only certain type of angles. There's a reflex angle, 2x. What is the angle at the circumference in the opposite segment going to be? X. Alright. What do you know about those two angles? 360. So look at this. 2y plus 2x is equal to 360 degrees. You all agree with that? If I divide everything with 2, I will have y plus x equal to 180. Do you see where there's a y and where there's a x? That means the opposite angles of a cyclic quad is equal to 180. Cool. Sharp, sharp. Next one. The exterior angle of a cyclic quad. Now you have learned a theorem in grade 8, actually in primary school already, of the exterior angle of a triangle. Right, the exterior angle of a triangle is equal to the sum of the opposite interior angles. Right. Look at this angle here. I'm going to put in a heart. Do you see the heart and the dot? They are opposite angles of a cyclic quad. That's the one that we just learned about. So heart plus dot equal to 180 degrees, ne? Okay. Do you see here's a heart and a dot as well? What will they be equal to? Why? It's adjacent angles on a straight line. So if this dot and this heart is equal to 180, and this dot and this heart is equal to 180, do you agree these dots must be the same? Because if this is 100 degrees, I know this one is 80 because it's the opposite angle of a cyclic quad. If this one is 100, I know this one is 80 degrees because it's adjacent angles on a straight line. So then I can say these two angles will be equal to each other. So the exterior angle of a cyclic quad will be equal to the opposite angle of the cyclic quad. Exactly as it is. Cyclic quad theorem's done. Tangent theorems. There are 3 tangent theorems. 2 of them very much easy. The last one is the only one that has a bit of a challenge. Right, so it's easy to see this one, tangents from the same point. Because tangents from the same point, if you ignore these dotted lines, you will see it looks like a clown hat. You see a party hat. Ne? So it's very easy to notice that that one is in your question. Right. Now the theorem says that when you've got tangents from the same point, then these two tangents will be equal to each other. Do you understand? Xavier. Did you like my child? Did you like my child? Okay, so it says these two are equal. This one we also prove using the congruency. So the first one, do you see the common side? OP is equal to OP, common side. Do you see the radii? So I've got another equal side in the 2 triangles. And now the third thing is actually we have to do theorem 8 before theorem 7. But theorem 8 will teach you that if there's a line from the center onto the tangent, this is called a radius. A radius on a tangent will always be equal to 90 degrees. So do you see there's a radius on the tangent? There's a radius on the tangent. Okay, so once again you've got 90 degrees, side, side. 90 degrees, side, side. Which makes these 2 triangles congruent. And that makes these 2 lines equal to each other. Now remember, when you've got 2 sides equal to each other, you're going to have a chord to have equal angles there. Do you agree with me? Okay, you will see that when we get to it. I just want to remind you. Theorem 8 has no proof. Nothing. We just know. The line from the center onto the tangent, which is called the radius. will always create a 90-degree angle. Okay? Last one. Now this is one that you guys struggle with a bit. So I'm going to turn it around and I'm going to show you first. When I've got a circle and there is a tangent and there is a chord, you agree, you see the chord, eh? Do you see that a tangent and a chord that meets each other, they create an angle? You see it? Okay. Now this theorem says that the angle that is created by the tangent and the chord will be equal to the angle that the chord subtends in the opposite segment. So not to this side, not this side. Here it's created, then to the opposite segment. If that chord subtends another angle, then that will be equal to the one that it created with the tangent. Does that make sense to you? Okay. We're going to practice it a lot, don't worry. But just see that the tangent and the chord create the angle. And then that same chord that creates the angle subtends another angle in the opposite segment, and they are equal. So the proof of this one, what we are going to do is, let me just check which one we're going to use. Oof, this is a confusing one drawn here. Let me start here. Okay, so I will call this one, let's give it a circle. I want to prove this one. Can you tell me which angle it will be equal to? The angle between the tangent and the chord will be equal to the angle that the chord subtends in the opposite segment. Do you agree with that? Yes. Okay, so those are the two we want to prove equal to each other. Now that's very easy. You see the construction made there? Right. These two angles are 90 degrees because it's a radius on the tangent. This angle is 90 degrees, those two, because do you see the angle in a semicircle? Number 3, the one we've already forgotten about. But there's the diameter, it makes the angle in a semicircle. Now, you remember Karabu-Umbali theorem? Yes. Look at mom and dad TQ. Do you see TQ? Yes. TQ has a child there by A. I'm going to color it in. You see? Does TQ have another child? Here by B. Do you see it? It makes another child there. So do you see Mbali and that angle make up 90 degrees? Yes. And Karabu and that angle make up 90 degrees. So that other angle, they must be equal to each other. Does that make sense? Because this one is 20, this one is 20 because of Mbali Karabu. This one is 90 because of radius on a tangent. This one is 90 because of angle in a semicircle. So therefore this one will be 70, this one will be 70. Done. Okay. That's geometry theorems. Theorem 1.1. Now that you have these theorems in the back of your head, we're going to use them individually. Okay, so we're going to ease into it. When you were here in grade 8 and we learned about Pythagoras, I said you can only do Pythagoras if you have two things. The first is a 90-degree angle and the other one is two known angles, two known sides. Do you remember that? There was a reason why I said that a lot, because of grade 11. We need to calculate this side x. Can I do Pythagoras in this triangle here? Why not? I only have one side and a 90-degree angle. Now in this information they tell you that PR is equal to 6. Do I have two sides right now? No. I have this side, and I have PR. I'm talking to or about triangle PQO. Why do I divide it by 2? Because of theorem 1. Do you see that? Theorem 1 said if the line from the center is perpendicular to the chord, then it bisects the chord. But do you agree with me if today is Friday and I ask you to do the sum, previous Friday, you don't have two known sides. I'm saying that because I want you to understand when you are using a theorem. Just because you know that this is 3 and this is 3 doesn't mean you don't have to prove it. You have to prove it. So before you can do Pythagoras, you need to start with that. Okay. So I'm going to say PQ is equal to 3. It's not given. If it's not given, I have to prove it. Now I'm going to say line from midpoint perpendicular to chord. Now I'm just saying in mathematical language that it bisects it, by saying PQ equal to QR. Can I now do Pythagoras? Yes, so now I can just say PQ squared plus QO squared equal to PO squared. 3 squared plus 4 squared equal to PO squared, PO equal to 5. Just remember to add that other reason, which is Pythagoras. Okay, look at number or example 2 so long. Remember what we need to do Pythagoras. Can I do Pythagoras? I need to calculate OB, you see, nay. I cannot do Pythagoras. Why not? I have two known sides. They have shown me that this one is equal to this one and the whole one is 16, so I know this one is 8. Why can't I do Pythagoras? There's no 90-degree angle. Do I know that there is one? Is it given? Then you must prove it. Okay. So I'm going to say OB perpendicular to AC. Why can I say that? Line from midpoint bisect the chord. Are you good? That's theorem 1. That's the way we use it. So it normally goes along with Pythagoras.
When we have to prove particles A, B, and BC, of these how we prove particles analytically, we still have to prove it.
You still have to prove?
Like the first question that we've done, like we have to prove PQ and QR.
Equal.
But it's also here, but it's also true.
Remember, the question at number 1 was to find the length of x. The question at number 2 is to find the length of OB. So you had to use theorem 1 first before you can do normal Pythagoras to calculate the length of the side.
So we don't have to prove theorem 1.
No. This is the application. Okay. You now have the 9 things that I've given you to use. You don't have to prove that they work. I showed you that they work, so you don't think I'm lying. You're just going to use that. Okay. So now, for example, at theorem 2, calculate the size of angle x. Tell me what is the size of angle x. What is the size of x? Why? You see, we don't have to prove the theorem. We're just going to say x equal to 110, and my reason will be angle at center equal to 2 times angle at circ to show circumference. You're going to get used to the abbreviations, okay? Don't worry about it. Okay, now for example 2. That is a diameter, AOB. Do you remember when we have a diameter, there's actually an angle that we can know what the size of it is. We know that C is 90 degrees because it's an angle in a semicircle. But I want us to pretend to not know theorem 3 yet. Okay, let's just use theorem 2 to find it. Do you see BC, mom and dad, BC? It has the angle at the circumference 35. Does it have a child in 90, 80 as well on this sketch? Thereby, oh, it has it. You see it? What's the size of this angle? 70. Do you all see it? You understand it? So I can say B, O with a copy on C is equal to 70 degrees, and the reason is angle at the center equal to 2 times angle at circumference. Now that I know that angle is 70 degrees, I need to find y. There's something special about angle B and C. Sure, seems like the Euclidean is your thing, ne, Caravello? Yeah, you are doing well. She says these two must be equal to each other because these sides are equal because of radii. You see that? So angle B equal to angle C, and I want you to write down the correct wording that we're going to use here. We're going to say angles opposite equal sides. So we don't use isosceles triangle. We have to say angles opposite equal sides, and then you are welcome to put in brackets radii. Just especially with these examples, just so you know why we are saying it's angles opposite equal sides. And now, do you agree I can find the angle of y very easily? Because it's 180 minus 70, which is 110, divided by 2 is 55. And now you don't have to write all of that stories. You can just give the answer and then say it's the sum of the triangle. Easy, ne? Let's do theorem 3. The angle at the circumference of a circle subtended by the diameter is a right angle. Angle in a semicircle. Okay. I want to know what is the size of x. Who has a plan for me for us to calculate the size of x? I'm hearing C. What is C? C is equal to 90 degrees. The reason is angle in semicircle. What is x then? 30 degrees. Why? The sum of the triangle, interior angles of a triangle. Example 2. How easy is that one? I still have to prove something first. Do you agree with me? Because if it's not given, I have to prove it. What am I going to say first? Angle R is equal to 90 degrees because it's an angle in a semicircle. And then I say thus because there's no reason for this. There's no Euclidean geometry reason for us to find the value of x. Do you agree with me? It's just that they share the angle. So now I can say thus x is going to be equal to 48 degrees. Okay, we've still got a few minutes. We can start with the cyclic quad theorem. So you see, it's not hard, ne? Obviously, it's not going to stay this simple because we're going to have all 9 theorems happening in one, or only 2 of the 9, and then it's not going to say, now we are busy with theorem 1. Okay, so you're going to have to go search for that. This is now the cyclic quadrilateral theorems. I want you to look at example 1. Look at the 102 degrees and I want you to look at that D, the one at K. And now you look at me. The angle 102 is not at the midpoint. D is not a baby. That is a 20-20 baby and the 102 is a 90-80 baby. Do you see that? If you want to use the angle at the center, 2 times angle at the circumference, you need to have a center. You see this one has no center. Okay. So, let's start. You know we always do this in alphabetical order, ne? So that means we need to look for C first. Karabu, this is your theorem. What is C? Yeah, I saw you were sleeping. Do the rest of you see the Karabu-Mbali theorem there? K and M, mom and dad. It had L, which is 24. It also has another child, J, which is C. So what's the size of C? C equal to 24 degrees. Okay, there are different ways that we can write this theorem. Because this one does not have a chord, we cannot say equal chords, equal angles. Okay, So we're going to say angles in same circle segment. Okay, so that's going to be the abbreviation that we use, because that segment there, which is created by KM, subtends J and L. Alright, who has a plan for me to calculate D? I don't have M, so I can't use Karabu Umbali. She's saying 90 degrees, which would mean angle in a semicircle, which would mean diameter, which would mean midpoint. No midpoint. Grade 8. Grade 8. Triangle. Grade 8. The exterior angle of a triangle. So D is going to be equal to 102 degrees minus 24, because it's the exterior angle of a triangle. And therefore it's equal to, what is this one? 78 degrees. Okay, let's just quickly look at example 2. And this is something that we don't come across a lot in an exam, but just so you take note of this. They would tell you in this example that the two circles, A, B, C, and D, E, F, those two circles are exactly the same size. Okay? Now you also see that this chord and this chord, although not in the same circle, they are equal to each other. Now, when those chords subtend an angle in two separate circles, but the circles are the same size, then they subtend the equal angle. Do you understand what I'm saying? Because this thing might as well have been picked up and then reflected onto this one as well. It will give you the same angle. Right. So that would mean that, just tell me, which angle does AB subtend on the circumference? That means this one. And which one does DE subtend on the circumference? That F. Okay, so that would mean angle C is equal to angle F, because now we say equal chords subtend equal angles. You see the difference in when we use which reason. So I must try to find X that's at C or X that's at F. Do you, any one of you, see a plan for me to find the X at C or the X at F? Now you need to look at what you have, ne? Plan. Angle at the center equal to 2 times angle at the circumference. Do you all see it? So what's it going to be equal to? 60 degrees. Angle at center equal to 2 times angle at circumference. Alright, grade 11s, tomorrow we are going to look at the second and the third cyclic quad theorem, and then the tangent theorems, and then on Wednesday we're going to start throwing it all together. Alright.
Bye.